Alright guys, welcome to another Advanced Refrigeration Podcast E2 training. Today we're going to go over programming loop sequence controllers and why we actually use loop sequence controllers. So we're going to go into the E2, we'll go into terminal mode. We will log in. If it lets me. Okay, so we're going to go to menu. All right, this is off to a great start. The terminal mode seems to be acting up, so we may just do this on ultrasite. Okay, terminal mode is not working, so the joys of terminal mode. So we're going to do this on ultrasite. So if we come down here, let's see if we already have one programmed. It does not look like we do. So we're going to right click on the E2. We are going to add a new application. We are going to go down to choose loop sequence control. And we'll call it test. Okay. Okay, so down here, it made a new loop sequence controller, added application. Let me resync the site real quick. Yeah, terminal mode is definitely messed up. I need to reset the E2. Okay, so we're going to add the application. So we'll go through this. It's the same setup in E2. Control EU is going to be whether it's defrost Fahrenheit, whatever your process variable is going to be, PSI, delta PSI. Basically, you have all these options in here. So PSI and degrees Fahrenheit and delta degrees Fahrenheit are going to be your most common. Okay, disable filter. If you want to have the process variable filtered, you can. Filtering usually slows it down. Bypass PID, if you click yes, it'll give you a bypass value. If you click no, you can set up the float. Output on fail gives you what your output is going to be when there is a fail meaning the input's gone or something's gone. That depends on all what you're doing. I mean, if it's a liquid differential valve, you obviously want it to fail open. If it's a say a holdback valve, you want it to fail open. You want it to fail at 100%. You want it to fail at 0. So emergency AV out, same thing. Update rate. So on the E2, the update rate is 1 minute to 2 seconds. I always put on loop sequence controllers, I always put it down as fast as I can get it, which is 2 seconds. So that's going to be how fast it updates the process variable and updates the PID loop. So if you do not have that set very fast, you're going to get really choppy PIDs. So input, that is going to be your process variable, whatever you're trying to maintain. So say you're trying to maintain a temperature, it's going to be whatever temperature that is. So put main temp, occupied. That could be, for example, if you're doing a defrost differential valve, you'd use the occupied when the suction group calls for the differential valve to be on. That's your occupied signal. Set point float in. That could be if you're floating a set point. You need to vary the set point up and down. Emergency override. Obviously, that's just a pointer. It's emergency override. So if you want to override it on or off, direct acting, off or on. Now this will change how the process variable reacts to the set point. So if you want the process variable to increase when your difference between the set point error increases, then you're going to put that as direct acting. If you want it to be reverse acting, you want it to decrease as the error increases, then it's going to be off. It's going to be indirect acting. Now this matters. I mean, this just matters how you have it set up in your actual, whatever you're controlling. I mean, if you're controlling a valve when the set point increases, you need it to close the valve, or if when the set point increases, you need to open a valve, or whatever you're controlling. So you go to set points. So you have an occupied set point and a non-occupied set point. So depending on what you're doing, so say like we're trying to maintain this discharge air temp at 68 degrees, but say at night I only need 64. So when I'm in unoccupied, I'm only trying to maintain 64 degrees. So loop sequence controllers are great for controlling valves, anything that's a floating actuator, floating values, controlling ESR points. It is a PID loop, basically. A loop sequencer is nothing but a PID loop. You're assigning an input and you're able to control something varying, whether it be a digital compressor, a VFD. You're controlling something variable with that. So this is a E2's version of a PID loop. So you have a fallback set point occupied, fallback on set point occupied, float in high, float in low. So that if you're using a float, okay, so float high, you may say, we'll say 69 degrees. Float low, we'll say 67. So it can float in between there if the floating is active. Float out of range, never use that. So outputs. So this is going to be your output. And then same thing, active set point. So if you were floating the set point, that active set point, you could write it to something, whether it's sensor control or something like that. The actual output is going to be your variable out, whether it be going to an ESR board, a analog output card, driving a 0 to 10 or 4 to 20 milliamps. It's going to be your actual output, or it could be going to some other application in the E2, driving something. You also in this have a Pwm sequencer, so you could do, say, 10 stages. Nope, it's not going to let me say 8 stages. Okay, so you could do a sequencer. So you could have, so it's 0 to 100 on in, so you can make minimum 1 or whatever. You can make it whatever you want. Sequencer max 100. Stage delay, so you can go 5 seconds per stage. So once you hit that, it'll start staging things up at 5 seconds until it reaches 100%, looking at the control value, which is your input. So this is something I would use for like heat strips. You're staging heat strips on this way. You could stage solenoids, I guess. If you were trying to do like a startup on a rack, I mean, this would work okay for like a CO2 rack if you were doing, you were using this loop sequencer to stage on circuits to simplify this, so it's not a flexible combiner. You could do the startup once it's engaged. You could use this as the startup, and you could start one every like 5 to 10 minutes. You could engage a circuit, and you could have it set up for that. So it's going to have your different outputs in there. So then you have your PWM periods. You could also do pulse width modulation with this. So you would need a digital output card where it could pulse the relays. So you could do door heaters. You could do some solid state relay stuff. I guess you could, if you got fancy, make your own digital compressor with this PWM. I don't see why it wouldn't work. So there's that. I don't do a whole lot with the PWM stuff. Little bit of door heat stuff here and there, maybe some lighting on occasion. Like I said, we don't do a whole lot with the PWM. Most of our stuff is going to be with the loop sequence controller. So when you set up the PWM, you could also set it up for all the stage outputs. So stage 1, stage 2, stage 3, stage 4. This is where like starting up so if we change this to like 5 seconds, and you change these to like this is AO1, AO2, AO3, AO4, AO5, A6, AO7, AO8. Say if you wanted to stage up a rack like after a power outage, and you were killing the solenoids or the circuit enables, you had these tied to the clean switches, and as soon as the rack comes on, you let everything kind of pump down, and that way you don't slam a rack on right away. Great application for that. It's about the only application I use the PWM setup. It's a lot easier than writing a flexible combiner that somebody's going to have to look at. The PWM's a lot easier to troubleshoot. So there's that. So then we get to the PID. This is probably the most less understood thing about CPC. Okay, TR range. That's going to be your error around. So you have your process variable, meaning your input. So your input's 68 degrees. Okay, that's your set point. Now you have your throttling range is the error on both sides. So if it's 2 degrees, 1 degree up would be 100%. 1 degree down would be 0. So that's that range in there. So 18. So 9 degrees up, 9 degrees down. So that's when it floats. The lower you make the throttle range in CPC, the faster the valve reacts and the PID reacts. The higher the throttling range, the slower the reaction to error. So a lot of loops you could tune just by tuning your throttling range. I mean, you don't need a crazy high throttling range for most stuff. I mean, for temperature control, usually I try to keep the throttling range a little lower. 18 is a pretty good number to start with, but it depends what you're working on. If you're working with pressure, I mean, it can go pretty quick. So like I may go for like a 20 throttling range or like a 10 throttling range. Okay, throttling range is your error at set point at which the valve is the value is 100% and 0. So just think about like I said, if it is 2 degrees, okay, or 2 psi. So 1 psi above set point is 100% PID. 1 psi below set point is 0 PID. So that's the range in which it has to operate. So PID out at set point, this really depends on what you're controlling. I mean, it's all going to depend. I mean, if you want your PID, if it's like a solid, usually like 30%, maybe I'll set it at 30% at set point. It just really depends on what you're controlling. If it's temperature, it may swing a lot. If it's pressure, depending on what it is, it could swing, it could not. This all depends on the application. Okay, now we're getting down to the PIDs. So D gain. So that is going to be your error correction over time. The D gain is basically like a predictive error over time. So we don't use the D gain in pretty much anything we're doing. So most of the stuff in HVAC is going to be PI loops, not PID loops. I mean, we're not using the D gain. We really don't need it for 99.9% of the things we're going to do. So I generally do not even mess with the D gain. It ends up causing more problems than it solves. So we're going to spend most of our time talking about the I and the P gain. So the I value is going to be error over time. So this is going to add to your set point error over time. So it's going to look every time the loop runs. So if the I gain is 1, every time the loop runs, it's going to multiply by 1. So if the error is at 12% and the PID is 12%, okay, it's going to add 1 to that. It's going to add 1 to that. It's going to add 1 to that. And what the I's value is, the I's job is to bring that error back down over time, because as that error creeps up, the I is there to creep it back down. So your I values, I generally start very low with them. So when you start adding I in, you could spin a loop up really quick. When I say spin a loop up, I mean, once you get a loop over 100%, so say it's at 100% and it keeps having error, that loop can go over 100%. It won't show on the controller, but it is. And it takes time for it to unwind and spin down and come back down. And like usually when that happens, it starts overshooting because your process variable will eventually come down. And then that loop has to bring that PID value down, and it ends up causing this nasty valleys and hunting. Okay, so we'll talk about that more in a second. But the P value. So the P value is is going to be your reaction to error. So what the P value is it's just trying to bring the error down to set point. So say your P value is 1, okay, and your error is 10. It's going to multiply that by 1 every time. So the loop runs. So what it's trying to do is it's trying to basically bring you in that throttling range. It makes peaks and valleys basically. What it does is it's trying to bring the error back down to set point. So it keeps bringing the process, it keeps multiplying by the error to try to bring you down to set point. So say if you're at like 12% of error, so 12 degrees of error, it's going to keep multiplying that by 1 in order to try to bring that error down. Once it does, it's going to overshoot. So the P value is going to cause peaks and valleys. You want to try to get it as close to almost flatlined as you can when you're tuning a loop. Generally, I start off with no I, and I will just start with a P gain, and I'll start with like 0.2 of P. I mean, we generally don't need super fast loops. The faster you make a loop, the faster it's going to spin up on you. So generally, I'll start low with a P gain. The lower you go, the slower it goes. So it really depends on what you're doing. And I will watch the loop. And if it's overshooting around the set point, like big time, I'll start increasing it so it gets a little bit faster, so it reacts a little better. Once you get it to where it's within like a degree or 2, or maybe like 4 degrees of around that set point, what you're going to want to do is start adding some I in. It's a little bit, you start with like 0.20 of I. You add 0.20 of an I. What that does over time, it starts to add I or subtract I from the equation, and then it starts to smooth out the equation. So instead of this choppiness now, you get this nice, even, like straight line almost. So that's how you're going to want to do it. Like I said, we don't really use the D gain. We're going to do a separate PID explanation. We'll spend a podcast just talking about PID. I mean, you could talk about this all day long. Every controller is different. Every application, has PID set up differently in it. Meaning, like Microthermal's PID is completely different than Emerson's. Dixel's PID is completely different than Emerson's PID. So some PID loops, bigger numbers are faster. Some PID loops, bigger numbers are slower. So it all depends what you're working with. So we're going to go over this for now, but PID minimum maximum, I use this on occasion when I'm trying to limit a loop. So if I don't want it to ever go to 100, so say like the most I want this valve to open up is 70%. So I'll go PID max 70%. What this does is it lowers the range in which it has to work in. So it makes the error that the valve could go less. So it makes it a little bit easier to control when you're controlling that range. PID minimum, if you don't want a valve to close 100%, say like you need a 10% minimum outside air temp in a damper, or outside 10% minimum outside air damper. So you would set that value to 10%. So it's never going to go below 10%. So even if you overshoot your set point, it's not going to close that damper more than 10%. That is helpful for stuff that you don't want to close all the way. So like say you were doing like a DDR valve and you don't want it to 100% close and high head the rack. So you would set a minimum on there of 10%. Now this bypass function, this comes in handy. So you could use this bypass function for a couple things. So I recently did this with a liquid differential valve. So what the liquid differential valve is doing, so when it's not calling for the liquid differential valve, I turn the bypass value, I have it set to right off the E2 down here at the input. So I went to a pointer, brought up the enhanced suction, and tied to the group line solenoid. And then I put the input at 100%. Okay, so when the E2 is not calling for the group line solenoid to be on, it's going to be at 100%. The reason I did this is because I wanted the valve to be open 100% all the time unless it's calling for it to run. I don't want it to have a differential when it's not calling for it to run. The power, I generally don't ever use this, the power setup. So if we go over to here, we got our inputs and outputs. This basically is just showing you all the inputs and outputs. Okay, so we're going to hit OK. We're going to start the loop, and I'll show you what it looks like. So graphical status. This is going to bring up a block logic status, okay? So you got your sequencer here. If we're using that, you have your control value in, which is our variable. So this is going, if you look, this is block logic. So you're going to follow it down to the PID input. Okay, we have a set point. So we have an occupied set point of 68 degrees and an unoccupied set point of 64. So this is going into a selection block, okay, with an occupied signal. So we are occupied right now. So we're going to be using our occupied signal. So you see right here, the set point out is 68 degrees. Okay. Now, you can see right here, we have a PID loop. Okay. So we are at 63%. See how it's going up? 64%. It's going up because we have a occupied set point of 68 degrees. We're at 67 degrees. So it's trying to bring that value to 68 degrees. So it's increasing. So see how it's increasing very slowly? So it's increasing slowly over time because it's just a P loop right now. So, and then if we had a filter down here, you could see how the filter is out. So right now that loop would be spun up 152% if we were using a filter. So we have no overrides right now. So right now our PID output is 67%. Now, if we were to take this and say edit application, and we took this PID loop, so we had a gain of 1. So if we went a gain of 0.5 for the I. Okay, so see our PID went down. So now it's going to react slower. So our loop is slowly spinning up. Now, if we take this and we override this input, so we put this input and override, and let's say we make it 50. So let's increase our error. Okay, so see how this instantly went to 100? Because we're way over our error. So if we made this 69. Okay, so see how the loop's spinning down? It's going down now. So we are a set point, we're a degree over set point. So set point is 68 degrees, and we are slowly going down. So it's slowly unwinding the PID. So the I value is not doing much because, I mean, we're only a degree over set point. So, or the P value is not doing much because we're only a degree over set point. So there's not much error, but the I value is creeping this down over time. So that's, see how slow it's going? So if we were to take this and put the I value to 1, see, it's going faster now because that I value is at 1, and it's going to decrease that loop more over time now. So say we change the set point. So say we change the set point to 70. See how we're increasing now? So we're only a degree above set or below set point now. So now we're slowly creeping up. So you can see how adjusting those numbers, affects it. Here's the problem with tuning PID loops with overrides. I mean, it's kind of difficult. We'll mess with the TR range real quick. So if we bring a TR range down to 5, you see how much faster this is going to spin up. Whoa, what did this thing do? Okay, see how it's at 100? We're only a degree above set point, but we're at 100. So if we took this out, so we're still at 100. So say we bring it to 70.1. See, it's not doing anything because we're just on the cusp of that error. If we bring it to still on the cusp of that error, so if we bring it to 71. We slowly keep creeping it up. We go 73. See how fast it's winding down now? It's reacting so much faster to that error and set point. Once we hit over that throttling range. So like I'm already at 0. So if we go to 75, see how I'm 5 over set point. See how it just started stepping up real quick. It's already at 35%. So the faster you increase, or the lower that throttling range, the faster it's going to react to errors and set point. So just remember that. I mean, a lot of PID loops could be fixed with just the throttling range before you start messing with PI loops. Like I said, start out small, adjust your throttling range. Generally, if you're doing anything with like air, if like, so you're doing like a VAV box, like 25 or 30 is a good starting out throttling range. If you're doing stuff with like a liquid pressure regulator, DDR, I mean, I usually go like 15 for a starting throttle range, and then I'll mess with the PID. So I'll try to make it work from there. It all depends on what you're doing. Like I said, this takes time to learn this and actually set this up and figure out how to tune these loops. Generally, you can't do it with overrides because, I mean, it's kind of a pain. Like you see, like I'm kind of messing around with it just to see what it would do. I mean, play with it. But here's the deal. So, like, in order to tune a loop, you need a live variable, and you need to be steady. So, like, if you're doing defrost differential valves, you need to test it with nothing in defrost. You need a steady rack. You don't want the suction, the compressor cycling on and off. You don't want condenser fan motor cycling on and off. So try to keep the suction as steady as possible when you're doing it. Keep the rack loaded up. That way you could tune this loop how it should be running, and then check it after, while everything else is running. So it all depends on what you're doing. So you just got to take that and, run with it. It takes time to tune loops. I mean, everything is different. With microthermal, it's different. With Emerson, it's different. With Danfoss, it's different. With RDM, it's different. It all depends on what you're doing. Just read their literature and how they define PID loops and how they go about adjusting things. Like, for example, Dixel, you have a TR range and you have an I value. You have no P value. Your TR range is your P value in Dixel. So, and it's backwards. The higher the number, the slower it goes. The lower the number, the faster it goes. Whereas in like Emerson's like loop sequence controller or the suction group or the condenser or the ESR value, the lower the PID loop, the slower it goes. PID loops are found in everything inside the E2, from the condenser control, from the ESR application to loop sequence controllers, to all kinds of stuff. Condenser controllers, air handler applications with blowers and how you speed up your blower and slow it down. It's all in there. So you just got to read the directions and go about it. We're going to do a podcast on PIDs. I am not the best with PIDs. It takes me a while to tune loops. I can do it, and I do it pretty good. But, I mean, there's tons of guys out there that understand it way more than I do. It's not all magic. There is a math to this. You could sit down there and figure out the math. There's some really good links on there. Like I said, I'm not the best. I can tune loops pretty good. It just takes me a little bit of time and, to break it down and figure out how it goes. And a lot of it's just sitting there watching how it reacts over time, watching how, it reacts when I change the process variable, meaning the input, watching how it reacts to different set points, watching how it reacts, when I make slight little changes in PID. I start out at 0.20, same thing with the I. I won't start at an I of 1, I'll start at an I of 0.5 or 0.20, and I'll slowly start increasing the P and the I. I'll start with the P till I get the graphs to stop. See if I can pull a graph here. Maybe I could show you guys kind of what it looks like. Get logs. I think I could do it this way. Because this should be graphing for a while. Okay, so obviously this is my house. This is the setback at night. It goes to 65 degrees. My wife jacks the thermostat up during the day. So if we look right here, so this is a process variable. So you can see the spikes down. 65 is your low, and your highs are 65.3. So this thermostat has 0.3 of a deadband. It's maintaining 0.3 of a deadband. So we'll do this. So generally, when you graph these, you'll have a set point through it. You'll have two lines. You'll be graphing set point, so it'll have a set point shot through the center, and then we'll say, for example, our set point is 67 degrees. So at 67 degrees, 67 degrees, we'll have a line shot through the center right here. Okay, then we should be, following that line. You can see this thing's overshooting. So she has it set for 67. it's overshooting almost to 67.5. You know, it's got ups and downs, ups and downs. This is the error in the PID. This is the PID in the thermostat. Believe it or not, the thermostat in your house has a PID loop in it. You know, it's deciding when to turn on and turn off. It's a cut in, cut out type of deal. So it may have a dead band of like 1 degree or like half a degree. It looks like it's about a half a degree dead band. So you see it goes up and goes down. I mean, you want to try to smooth that out. You don't want those peaks and valleys. See, they go up and go down. You want it to be almost flat and maybe like a tiny bump above and a tiny bump below. I mean, you're never going to get it perfect. I mean, for what we're doing, we don't need that. We're not like controlling conveyor belts and robots and stuff like that. I mean, we're controlling temperature and pressure. I mean, we have, you know, a degree or two or a PSI or two of leeway on it. So that is how we do the PID loops inside a loop sequence controller. I want to see if I could try to get the terminal mode up right now. I'm not really sure what's going on with it. Probably gonna have to reboot the controller. Yeah, it's not letting me do anything. I mean, this is an older E2, and I've pushed a lot of stuff in it for you guys in the last couple weeks. So hopefully coming up here pretty soon, we're going to have an E3 in here if we can get Emerson to donate us one. And I will start making training videos for the E3. But that is a basic loop sequence control. Like I said, a lot of this is custom. I've done custom drive stuff with it. I've done my own pump skid control with it. I've done heaters with it. I've done defrost differential valves, holdback valves, receiver pressurization valves, dampers, anything that's going to be variable and it's going to be outputting a variable output, meaning a percentage. You could tie it to ESR points. You could tie it to the ESR points as an input. So whether you wanted to drive a valve, whether you wanted to, like this one, I'm doing a DDR. So I have a DDR set point. So it's EPR valve. I have a DDR. You could, any variable output, you're going to use this, or any like staging output, like a CO2 restart, you could do with this without using a flexible combiner. Let's face it, most guys are afraid of flexible combiners. It's a lot easier to do it this way. So thanks for watching, guys, and appreciate it. Catch you in the next one.